Share screen.
So Bracker and I actually had a question last night.
Oh.
We met a homework assignment. But can we just kind of go over the kill function in general? Does it actually kill?
Okay,
Or is that
I mean, that's what we're talking about today. But based on your starting point here, let's talk about the high level of kill, because kill has kind of two. Let me get down here. I'll just see. I'm going to add some stuff to this slide, so I'm not going to steal that yet. Let me do this and this. All right, so kill command. And this may be an interest, I'm sharing my screen, right? You can see it?
Yeah.
Okay. So kill command, this kind of creates maybe an interesting reminder. Hopefully we've seen by now that C is very close to the OS in terms of its capabilities. So the C programming language was kind of created for writing operating systems, and we're almost seeing like a reverse cycle here where our operating system has a whole bunch of system calls associated with it. So the OS has system calls associated with it, which are basically API endpoints that allow third-party, say, and other system calls to interact with the OS. So that pretty much means that most is maybe an unfair, many of the common commands that we might issue from the command line on Unix, in our case here, like kill, also exist as functions inside of C as long as we include the right library. Okay, so if I come out here and I run the man page for kill, and this is going to be the, actually I'm guessing it'll show up the command line one, so man kill. So this is not the C library for kill. This is the normal command line, whatever. And so first of all, the first thing that you asked is, does the kill command actually kill a process? The short answer is the kill command kills off a process given its process ID by default, but can also send alternative signals instead of kill. And then I'll say underneath this, similarly, a running process could choose to implement a handler for the default kill signal, or any other signal for that matter, where it does something else other than die. So we actually have things happening on both sides. The kill command, if you just type in kill and then a process ID, it's going to send the default kill signal to that process ID as opposed to a user-defined signal, something other than kill, some other signal. All right. Similarly, the process that's receiving that signal, by default, if you haven't done any special handlers or anything like that, the process that receives any signal, in this case, the kill signal, will kill itself. because that's the default behavior of running processes on Unix unless the process overrides it. So you can almost think of that as like historic object orientedness, right? You have this idea of a generic process running on the Unix operating system, and all running processes on the Unix operating system adhere to the standards set up by a generic running process. And one of the standards is if they receive the kill signal, it dies, it kills itself off. Now, a process could differentiate itself from a generic running process by implementing a handler for, in this case, the kill signal. So keep in mind there's a difference between the kill command. Let me come over here. I think I still have it up. Trying to think which is the actual signal sent by the close this. Unix signals. Get a list. One of these will just have a list of all the signals. So it's possible sig abort is the default kill signal. Sig interrupt, actually, I think is what the kill signal does do.
There was sig kill right there. I don't know.
Oh, there it is. Thank you. I wonder why that wasn't on the other thing. Okay, so this is the kill signal. So would make sense that that's what the kill command sends by default is the sig kill signal. So a process could have its own handler for sig kill where it does something other than the default, but the default for sig kill says this process is killed off. Now, I'm not sure what the default behavior is for a generic process. I don't know if it does any sort of memory management, cleaning things up. That's probably evolved over time for, you know, how does an indirect death of a process make sure it doesn't leave, you know, memory messes behind. So my gut feeling is that a modern Unix operating system, or any operating system for that matter, probably takes a little bit of extra time to kill off a process and does any sort of obvious mess cleaning ups in terms of allocating memory and things like that, so that when the process dies, it's not leaving in its wake, you know, some chunk of memory that's never going to be able to be given back. All right, but in any case, I'll go back out here. When I looked at the manual page for kill, this is showing me the kill command, which is a computer program that can be run from the terminal. And this computer program that somebody wrote, probably one of the Linux open source operating system people wrote. It's been around for a long time. Very, very, very likely sends a kill signal to a process given the process ID you gave it. So this kill command is taking in as parameters, among other things, at the very least, the process ID. So when you're looking at the way of reading these things that are in square brackets are optional. But this guy right here says the kill command requires at least one input. It needs to know the process ID of the dude you're trying to kill. All right, so this computer program will take as a command line argument, that's part of the main program, the argument count and the char pointer argc or argv, the values. It'll take in bucket 1, the process ID. Bucket 0 will be the command that was issued. But bucket 1 will be the process ID, and it will go and it will use the kill function, not the kill command, but the kill function, to send the default sig kill signal to this particular process ID. but you can give it an alternative signal to send. Instead of the default sig kill, you can make it send any signal to a process. And I think we saw that, at least in the examples early on here, we were sending sig interrupts. Was that here? Where they were doing the control C. So this sent a sig int command from the command line. So when we do control C, the operating system sends the sig int signal to the running process by default. And this guy handled that signal and then kept going. Instead of the default sig interrupt just saying, well, if this process didn't do anything special, I'm just going to kill it off. It dies. Does that make some sense?
Okay. Yeah, so it's like going to Home Depot because we know that we need a tool.
Yep.
So we're going to Home Depot and we see the kill function on the shelf, and we look at it and we say, okay, that's really close to what we want to do. We just don't want to do that last thing and actually kill it. So we can modify the handler a little bit, not to actually do that last thing and kill off the process.
Well, you wouldn't modify the hammer. So what you have
handler,
is your hammer, your kill hammer. It has two buttons on it. One button is to just kill and you give it the process ID. The other button is to send a different signal other than the default given a process ID. The thing you would have to modify, so I mean, you could modify the hammer by saying send sig user 1 to this process ID instead of the default sig kill. If you did that, then the process probably wouldn't die unless they have a handler for sig user 1 that said it should die. Alternatively, what you would do is if you wanted the behavior of a running process to be different than the default, I received a sig kill, I should die, you would have to create a signal listener with a handler for that process that says, if somebody raises sig kill to me, rather than doing my default behavior, do this alternative behavior instead. So in that case, you're kind of modifying the nail that you're hitting with the hammer, maybe in your analogy.
Okay.
So both of them have modification opportunities, right? The hammer, you can say, just do your default thing or send a different signal by choice. And then the nail can say, well, by default, if somebody sends the kill command, that the signal is sig kill, but I might receive different signals other than that. So the nail can optionally choose to have signal listeners and corresponding handlers for any signal. But every single, to that point, every single process will have at least a default handler for what I'm guessing is the rationale behind what they showed in here. No, not in there, in here. Since they're labeling these as the standard signals, I'm guessing that the generic, think of it like objects in object-oriented programming. So at the top of your hierarchy, you have this object class that has all the default crap in it. So for example, in Java, the object class has that toString method, which shows you the weird looking memory addressy thing. And only if you override that, do you get something other than that. So my guess is based on this, that these are the generic signals that all processes, although this kind of goes against that, I think. The sig user 1, sig user 2. But in any case, whatever the default signals are, the core generic process, the equivalent of object in our operating system, it will have built into it at least one handler, let's say for sig kill, probably a couple of other handlers like sig interrupt and things like that, that has the basic behavior that all processes should be relied on to have. And if the process wants to distinguish itself from that default behavior, it can choose to do that by sending up a signal handler. But otherwise, all processes are guaranteed to be able to receive, in this example here. This process right here that we wrote with this guy up here, we specifically created a signal handler for sig interrupt, right? So we said, if you receive sig interrupt, call this handler. We wrote that as a special handler. But if I write a computer program, so let's say I come in here and let's do a new file here. And we'll call this guy test.c. And I don't even need to include anything special. So I'll just say int main. I actually don't even think I need to give anything in there. And I'll just say while one, do nothing. So this is a program that'll just be an infinite loop. No, this is not VI. And I come back out here. Where am I at? Actually, I can do it from in here. What is it? Control tilde. Oh, later. Yeah, control tilde opens up a terminal in here, although it didn't even open it up in a better place. I don't like that. We'll just go to it from out here. So there's our GCC test.c. We have our a.out. So this is an infinite, that's all that program does. It creates a while loop and just sits there and spins. All right. I wrote no signal handler or anything in here, right? This is just, this is that whole program.
Genius.
But I can still do Control C and it'll exit out, which proves to us that the default generic running process on, in this case, Ubuntu, but this comes from Linux. This is not Ubuntu is a distribution of Linux. This has been something that's been around forever. The default running process knows how to handle a sig interrupt because Control C, this guy right here, is the sig interrupt signal. And indeed, this program did die out, right? It exited, got us out of that while loop.
Yeah.
Okay, so it had that handler, even though we didn't write it. So now,
yes. Then if you wrote,
go ahead.
If you wrote a handler for a sig interrupt that said like print out hello world to the screen, when you did that, it wouldn't kill it. It would just print that out and then keep looping, right?
Right. Yeah. So if I do
Okay.
this, I have to put a couple other fancy schmancy things in here, but we can make this guy work real quick. Do this. Actually, it's going to be interesting whether it can get a word in edgewise if I don't sleep, but it'll be fine. I think it'll work fine.
Oh, is that why they wrote that loop like that?
Probably to give you a more a quicker, like you noticed it stopped kind of right when it did it or within a second, because with the while loop running, this guy right here, I mean, there's no interrupts there. So this is just going to get its whole time on the CPU. So this will actually be an interesting test to see the performance of the interrupt handler for signals. I bet you it happens immediately. I think it'll be fine. All right, so, well, here, we're just inside the handler function. We can just make it say that, no problem. All right, so we'll compile it again, we'll run it. So again, it's in its while loop, but in this case, it's registered itself to have a handler. This is a little bit sucky since now we don't have a way of killing the process. We'll have to externally kill the process. So now we've written a handler that isn't the default one. So if I hit Control C, we get the inside the handler function. So it's not dying off the way I want it to die off, right? because I've written a more local version of that handler rather than the default, hey, I should die.
Okay, now this
With that
is
in mind, then,
making sense.
how do I kill this process then with that in mind?
Well, if you close out of the terminal, won't it kill it?
Actually, that's probably true. If I do close the terminal, there is a sig up, which is a hang up signal that I think the terminal sends to it if it closes. So since I didn't write a handler for that, I mean, you probably could write a. Actually, it's kind of interesting.
Seems like a good
Could you
virus.
write in a, I think you can. I think you could write an immortal process. So if you determined all of the different signals that might get sent to it by the operating system, and what the default handler did, you could create handlers for each of those, that just kind of gave like, I don't know, like maybe spit back out bad words or something like that. Like, yeah, you think you got me, whatever.
Well,
and it just didn't
there
die.
actually is an app that it's called a Desktop Goose, and it's like a virus. It's like a fun virus you can like download on your friends' computers. And whenever you try to get it by like, closing out the app with Task Manager or anything,
Right.
it just like prints out like a stupid message.
Yeah. So the only way to get rid of it is to reboot your computer. Don't run it again.
Yeah.
But in this case, I think I can probably just go to, I opened up a second tab. I can go to top. I can probably find my a.out process. Well, here, I'll just do ps-ax pipe to grep a.out. So this is our process ID is 13571. So I'll do kill. Well, actually, this is funny. Kill 13. Oh, this will work. Because I'm not sending the interrupt to it. I'm sending, if I do kill sig int, let me look up the, ooh, this is a nice one. Kill -9, kill all the processes that you're able to kill. That would actually be very handy in some of the, hopefully some of you noticed when you were working on the lab that sometimes you can, your child processes can get out of control where everything slows way down because you got a 4 zillion child processes going. But in this case, it's kill -9. I'm guessing kill all is equivalent to kill -9. All right, so kill -L capital will show me the things I can send it. Oh, so I already know. So we're gonna do a kill -L sig int, but I think we saw it was sig t int for terminal interrupt, but let's just try it with this 13571. What? Sig int. I sent that. Invalid signal specification. Oh. How do I kill with a command? Kill with the options and the process ID. Okay. Oh, that's not the, oh, it's -S for the signal. L just shows you the list of signals. So I'm sending, oh, that's still the T int. Would he die on its own or is that the wrong? Oh, it did die on its own. I guess the operating system killed it off. So we'll run that again here. Let me just get back to my, so it is 14498. Now this guy should have gotten into his handler externally, but now I can send the sig. Actually, I can just do kill like that, and now it should have actually died because I sent a different signal to it. That makes some sense.
Yeah, that just helps a ton. Thank you.
So that kind of goes back to what I started talking about today, but also your initial question. This is the what does the kill command actually do? And maybe to your point, it's a little bit, it's named unfortunately. Like maybe a better name for it would be like send signal, right? And maybe there's a -K option which sends the kill signal. Because in this case, what they're doing is they have a command called kill, which to a human being, we look at and say, well, this sounds like it probably just always kills. But the reality is it doesn't have to always kill. We just saw an example over here where we use the kill command to send a different signal than the kill signal to this process ID. And we might say that this doesn't sound like a very good program name for something that can do something other than kill. But that's the way it is. The kill command does what the kill command does. I am interested in seeing if they have like a send signal. Yeah, there is a signal command. So if I do man signal. Oh, that's actually, it's signal is just the C library that goes along with kill. Yeah, so it seems like it's just one of those historic commands that maybe when it first started only knew how to kill. And then at some point they decided, you know what, we have these other kinds of signals that we've now added to the operating system. How do we, by what mechanism do we send other signals to it? And then somebody said, well, kill already does exactly what you wanted to do. It just by default sends the sig kill. Probably before there, it probably wasn't even a sig kill. It probably only was one signal, and that was to kill. But then once they added signal handling, they decided, well, the kill command already sends a signal. Now we can just let them specify the signal, which is with a -S option. But it is a little bit unfortunately named. Okay, so this is what the kill command ultimately does, and we are dealing with, let me do something on the screen before this. So yeah, so the idea here is that C is very close to the operating system, and we just kind of saw that just through those man pages thing where the kill command at the operating system level is closely related to the signal.h library for C, which allows you to create handlers for different things. Okay, so actually I'll go back into man signal here. And that's for a handler. Actually, let me do man raise. All right, so we're looking today, and we'll get as far as we can. And I'm not giving you, well, I'm not officially giving homework over the weekend unless you're not going to the hackathon. So make sure if you haven't signed up for the hackathon that you have followed the link in Slack to sign up for it. So I'm going to say raise versus kill. Function in C. So I want to specify that we're talking about this stuff inside of a C program. So this is not at the terminal because we already talked about kind of the confusion with, actually the confusion leaks into C too, doesn't it? Because the kill function inside of C also allows you to send it, to give it a different signal to send. But we're talking about both of these in the context of inside of our C program. So raise sends the signal to the person who called raise. All right, so this is them sending a signal to themselves. Okay, so function sends a signal to the calling processor thread. So if we're dealing with a single threaded program, this is equivalent to using the kill command, sending something to yourself, your process ID. We haven't talked about threads yet, so don't worry about this. But threads are different than threads are kind of the alternative to fork. We've been looking at the fork system call. The fork system call actually creates a completely separate process, a brand new, full functioning duplicate clone of the current process at the operating system level that has all the same rights as any other process in terms of getting CPU time and all that stuff. Whereas a thread is you can think of it as kind of a sub process of the current process. So a thread does not exist as an independent entity at the operating system level. It is managed by its parent process, the process that spawned off the thread. From a programmer's perspective, in terms of the capabilities of the two, we can think of them as being relatively similar, where we are creating a second worker to do some additional work asynchronously to our current work. So we're, with the fork system call, we're cloning ourselves, and then we're asking a question. If I'm the parent, I should go do this stuff. If I'm the child, I should go do something else. And both of those things are happening, let's call it pseudo in parallel relative to the operating system scheduling it on the CPU. But at the very least, they're not blocking each other. Both of those things are happening as fast as they can happen, independent of each other, based on their ability to get CPU time. Where we had that same setup and the process created new threads. Now what we're doing is we're saying, well, these things are happening pseudo in parallel, pseudo simultaneously, but the threads are not getting their own CPU time. They're instead sharing CPU time with the parent. So if the parent, I'm just going to use big numbers that make it easier for us to follow in human time. If the parent gets 10 seconds on the CPU and they spawn off 10 child threads, well, let's say 9 child threads, then the parent and each of its 9 children would likely get something like 1 second on the CPU for each time that the parent process gets the CPU time. So the parent process would get to do some of its stuff for a second, and then each of its children would get to do some of their things for a second before the process gets kicked off the CPU. All right, I'm using big numbers there to kind of put it into human timing, because that's not how computers actually work. They're happening, you're getting some number of microseconds or some number of cycles on the CPU, which are happening in the blink of an eye, divided by 100,000 type of situation. But threads and processes are different, but they're very, very similar. And hopefully you talked about those in the 350 class, the difference between threads and processes. Is that an accurate statement?
I remember talking about threads.
You had to have talked about processes in an operating system class. I think even with effort, you couldn't have avoided talking about processes. Although that would be really.
I mean, I think like briefly, but not.
So maybe they didn't create a correlation between threads and processes.
Yeah.
You weren't really talking about problem solving where you were spawning off multiple copies of either one of those.
Yeah.
If you're talking about the operating system level, the operating system manages processes. Modern
I think we did each, but we did it separately.
Okay.
Like we never went together.
That's fine. But the reality here is they basically both solve the same problem, just threads are a little friendlier to the operating system. They say, if I'm the parent process that's going to spawn off some threads, I'm going to share my time with my child threads, as opposed to what we're doing right now with the fork system calls. We're saying, look, I'm not sharing any of my time. I'm just going to spawn off children to my heart's content, and they're going to get their own time on the CPU. And this is all the operating system's problem to babysit my children as they're running rampant on the operating system. All right, but in any case here, this raise function, this sends a signal to yourself. Okay, it's how a process sends something to itself. And we're going to try to look at this. I'll actually do it inside of that test program for right now, since we already wrote that a little bit. So I'm going to come inside test here. And we will go ahead and let's see. I'm going to do sig handler parent. And we'll just write parent here like this, just so we know who called who. And we'll have sig handler child. And we'll say this is the child. Right. And then we're going to come in here and we're going to say, well, it doesn't matter. I can say PID. So we'll say fork if PID is equal to 0. I'm the child. I'll go ahead and register the interrupt handler for SIGINT being my child handler. Else, I must be the parent. I'll register my handler to call the parent handler, but for the same signal. And then what we'll do is we'll have the, we'll just do another one of our while one things here. And actually, just for the sake of convenience, I'm going to say sig user 1 for these. That way I can still interrupt the process by doing a control C to kill it. I'm just using a different signal number. So all the child will do is he'll wake up, he'll register a signal handler, and actually then he needs to, this will give us the opportunity to look at pause. Actually, I'm going to run it like this first, then we'll look at pause. All right, so we'll create a duplicate of ourselves. If I'm the child, I register my signal handler, and then I die. If I'm the parent, I register my signal handler, and then I sit there in an infinite loop. So let's see this guy run first. Let's see, what do I want to do here? I want to, I'm going to do this. I'm going to say raise sig user 1 inside the parent. Oops, that's not what I need to do. And then I'll sleep for a second. All right, so we'll create a duplicate. If I'm the child, I just create a signal handler for my child handler. If I'm the parent, I'll create a signal handler for my parent. Well, I register my signal handler for sig user 1. And then I go into an infinite loop where I raise the sig user 1 signal. And then I go to sleep for a second, raise the sig user 1 signal, go to sleep, yada, 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 yada. Okay. So what do we expect the output of this program to be when I run this? That's what the two handlers do, parent and child, just output inside handler. What we're most interested in here is the behavior of raise. So right now, the child's not going to get anything because the child says, okay, I'm going to listen for a signal, and then they die. So as of right now, we're not going to see anything on the child side of things. So we're inside the parent. Every 1 second, we get the thing from the parent. Okay. Now, the reason we didn't get this in the child, I go back over here. I'm going to, we're just going to say raise sends a signal to yourself. Kill sends a signal to a target given its PID, i.e. interprocess communication. Now, we do want to, let's see, I'll put it here. Note, pause function blocks and waits for a signal. All right, and just to prove what's going on right now is right after this, I'll do a printf, child is dying. So without putting a pause in there for right now, I'll go and run this again. And we see the kid immediately died. You know, he registered his handler and said, okay, I'm interested in a SIG user 1. And then he kicked the bucket, never to be able to handle it because he's dead. He's no longer on the operating system. There's no signal for him to receive, yada, yada, yada. Now, if I change this and I say child is waiting, and then I call the pause command, and then I'll say child is dying. Like this. So now we register our handler. We're going to say, hey, we're going to wait, and then we're going to pause. This says child should wait for a signal. All right. And only after we actually receive a signal will we say we're dying, after we handle that signal. So now I run this, and we see that the child is waiting, and we see that the parent keeps raising the SIG user 1. But the parent is the one who keeps getting that signal, not the child. So raising that signal only raises it to the current process ID, not to other process IDs that are also interested in that signal. In our code here, let me go ahead and do that. That's the reason why I said SIG user 1 instead of the SIG interrupt, is so I could interrupt it and kill it. So if I want, so this raise command here only sends the signal to the parent. So even though this child has said, I am interested in SIG user 1, and the parent is raising SIG user 1, the child does not get that signal. Only the parent gets that signal. Now, I could instead say I want to kill PID SIG user 1. This sends the SIG user 1 signal to the child. Because if I'm in the parent here, the PID I have is my child's PID. Right? When we do the fork command, fork returns a 0 if you're the clone, or returns the process ID of the new child if you're the parent. So when I say I want to send this signal to this person, this target, this child process, now the child will receive the SIG user 1 signal that he's been waiting for when he paused. Then he'll handle it. So he'll say what, child and handler, whatever. And then he'll say he's dying. Might need to sleep for a second. Because I'm guessing the process ID didn't exist yet. Let me just say sleep 2. There we go. I think we just saw a race condition effectively happened, where the parent tried to kill the child, send the signal to the child, but because it happened so quickly, the child process had not actually been created yet. So it had the process ID of the child, but the child didn't actually exist. Okay, it's kind of like having somebody's social security number for I don't know, a baby or something before they're actually born. I don't know if that's really a thing, but let's just pretend like it is. I don't think it is, but that type of thing. The parent knew what the process ID of their child would be, but that child didn't actually exist before. So I put that little weight in there, said, look, let the operating system, let's even put a comment here. Let the OS finish creating the child process. Then we could come in here and we can send that child process this signal. Kill off the parent, run this again. Child's waiting. 2 seconds later, the parent sent the signal specifically to the child. Child got the handler, and then the parent kept going. But the parent keeps sending that signal. So I can say, if not this, printf, my child is dead. I could break out. Because each time through this loop, the parent's going to try to kill their kid. And since the kid only receives the signal once with this pause and then dies off, eventually this kill command is going to return is going to get an unsuccessful. Child is waiting. Child is dead. My child is dead. Parent process ended. So the second time the parent tried to kill their kid, they recognized the kill command said, look, I sent this signal to a process that no longer exists. And we saw that at the command line earlier. Remember when I had to flip back over and we saw that the operating system had killed off our process that was in the infinite loop? Okay, so hopefully this is starting to become a little clearer how these signals are working and the difference between raise and kill. So we'll come back on Friday and we'll keep working towards the solution for the lab. So I'll, I guess, change the due date again or whatever. Yeah, just don't worry about it. No homework for Friday. I want to make sure we have a full understanding of this. So we'll hopefully finish that on Friday. But if you've not already signed up for the hackathon, do that as soon as possible so they have final numbers for food and all that stuff. All right, I'll see everybody on Friday.
Thank you for this, Whitman. This was really good.
Good.
This
Well,
helped me a lot.
everything comes out of my mouth is gold. But I am sorry we're having so many online classes. Hopefully we're back to normal next week.
This was diamond. This is better than gold.
This is diamond stuff?
Yes.
Well, good. All right. I'll see everybody on Friday.
Thank you.
Bye-bye.
See you Friday.